Hello all, welcome to this course on time series modeling and forecasting using R. Okay. Now we are sitting in a fresh week, and then again just to give you a very quick refresher as to what was covered the last week, so that there should not be any disconnect between, let's say, last week and this week. So of course this week is entirely different topic, but again just to make sure that all of you are through with the last week, right. So last week was predominantly based on, let's say, modeling volatility or modeling changing variance in the underlying time series, and there we sort of saw multiple different models, let's say Arch model or Garch model, their extensions like GJR Garch, E Garch, threshold Garch, asymmetric power Garch, etc. And down the line we talked about ARMA plus Garch models, right. And in the very last session, or rather the last session of last week, which was the practical week, we try to incorporate all the theory we studied in the last week and then try to implement them on a practical sort of a framework, right. And there, if you remember, we initially simulated from all the underlying volatility models like Arch 1 or Garch 1, Garch 2, etc., or ARMA 1, 2 plus Garch 1, right. And then down the line we analyzed one real data which was NYSE returns data. And one small homework I gave you in the last week is that if somebody is more keen in exploring about volatility models or modeling in general, then there was one other real data set which we did not have time to cover in the last session, which was Bitcoin data. So hopefully before you sort of start with watching this week's videos, again a strong suggestion is that again you go back and try to complete that code just to understand that how do you sort of place all the visual graphs and charts, and then how do you gather some information from, let's say, the actual model structure, right, and then let's say the model implemented on the actual data, then the forecasts, right. So all these things you have to be completely sure of, all right. Okay. So now proceeding ahead, so the topic for this week, this entire week, would be revolving around this idea of non-linear time series processes. Okay. So far all the processes we have seen are pertaining to linearity, or rather linear time series processes, because linear means that you have sort of a slightly simplified sort of a structure. Okay. So we started with ARMA, or rather AR models, MA models, then ARMA, then ARIMA, SARIMA, and lastly Arch, Garch, right. So all these models have a mean structure which is inbuilt in the model itself, right, and that mean structure could be either ARMA or ARIMA, etc. And both ARMA and ARIMA are kind of linear time series processes in a way, as it sort of captures the linearity aspect. So linearity means some sort of trend in the data or seasonality in the data, right. So these are some characteristics which are sort of corrected or rather modeled by ARIMA kind of a model. Okay. But as in how you have a slightly complex kind of a model structure, or rather a real data structure, a linear time series model won't do the job. So for that matter, a non-linear time series process would be slightly more useful. Okay. So in the entire first session, or other first or second sessions of this week, since the entire area of non-linear time series processes is slightly different, we'll try to focus more on how exactly can you sort of differentiate between non-linear processes and linear processes, and under what scenarios can you implement the non-linear time series processes rather than linear, etc. Okay. One more very important disclaimer is that if you are sitting in any time series lecture, or rather a course, right. So I'm not sure how many of you have done a time series course before this, but if you sat through and sort of completed the entire time series course in some of the earlier years of your education, then I am pretty sure that nobody touches upon the idea of non-linear time series processes. Okay. And again, why exactly? Because so understanding the nitty-gritties or understanding the technicalities is not that easy when it comes to non-linear time series processes. So people do, of course, involve all the linear processes like ARMA, ARIMA, SARIMA, right. Obviously they do include Arch, Garch, and also obviously there would be, or there might be one chapter on spectral decomposition as we had earlier, Fourier transformation, all these ideas. But covering non-linear time series processes is not a touched upon topic very much. So again, I am not saying that all the courses do that, but then again, the idea of non-linear time series processes is not easy to sort of understand or sort of explain. So people tend to skip this from their usual time series course. Okay. Okay, so just to give you a flavor of what kind of different processes there might be, and where exactly the linearity sort of fails down, and where exactly does one require the idea of studying the non-linearity in the time series or rather some non-linear processes is kind of important, which we will see in this week now. Okay. Alright, so first couple of slides would be a very brief introduction. So, the nonlinear time series analysis extends the traditional time series methods to account for systems where the relationship between variables cannot be adequately captured by linear models. Okay. So, again just to specify, just to push on this point is that wherever a set of linear models sort of fail, there exactly we make use of some non-linear time series techniques or non-linear time series models. Okay. So, again non-linear time series analysis extends some traditional time series methods to account for systems where the relationship between variables cannot be adequately captured by some linear models. Okay. And second point is that non-linear methods are crucial for modeling some complex phenomena in areas such as finance, climate science, biology, etc. So, all these would be sort of workaround areas or other practical areas where non-linear techniques or non-linear methods are kind of crucial. Okay. So, secondly we will try to understand that what exactly are the characteristics behind this entire non-linear set of models. Okay. So, obviously the very first important point is non-linearity, of course. So, relationships between variables are not additive and may depend on interactions or certain thresholds. Okay. So, whenever it comes to additive models, we will try to assume that additive models are sort of linear in structure or they can be sort of transformed to a linear kind of a structure, but wherever the relationships are not additive between the variables and may depend on some interaction. So, interaction means two variables are interacting, which means that one of the variable affects the other in some sense. So, in a way they cannot be added or their effects cannot be added as both the variables are proportional. Okay. So, in that case they have to be multiplied. So, such multiplications are called as interactions. Okay. So, if the relationship is not purely additive and may depend on some interactions or certain thresholds, then non-linearity comes into picture. Okay. Secondly, obviously complex dynamics. So, these may include some chaos, bifurcations or periodic behavior, right. So, if you want to analyze some complex structures underneath the time series or the practical data set, then obviously putting forward a linear kind of a structure will not make sense. Okay. So, one has to shift from a linear structure to a non-linear structure. So, again just a small disclaimer is that this entire area of non-linear time series is completely different from analyzing linear time series, right. As in how you have to, so exactly the press is more on how do you sort of make the model structure slightly more complex or rather be capable of sort of incorporating some complex dynamics of the time series. Thirdly, state dependence. So, what do you mean by that? So, current values might influence some of the future values differently based on the state of the system. So, this is called as state dependence. So, based on which state the current time series is running in. So, again imagine that you have one practical time series broken down into different states, okay, and then again all the states are not exactly same. So, you have some differences between states, and as in how the time series transitions from one state to the other, you might require a slightly different model structure. Okay. And it also means that the current values might have the capability of influencing any of the future values differently based on the different states of the system. Okay. And obviously, the last important point is non-stationarity. So, the statistical properties such as mean or variance may change over time. Okay. So, of course, all these are mere characteristics as in when one might have to look out for some non-linear time series processes rather than linear structures. Make sense? So, hopefully, by this time I have given you abundant motivation as to why one has to shift from a linear structure or rather a linear model to something like a non-linear time series process. Alright, so again just a slide to start with is that can you discuss some examples of non-linear processes, and the answer is yes. So, all these are examples of some of the very important non-linear processes in the literature. So, the first one is threshold models. So, what do you mean by that? So, a very useful or very widely applicable model in this context is the threshold autoregressive or in short TAR model or TAR model. Okay. So, for example, the threshold autoregressive models where different dynamics operate above or below certain threshold values or certain threshold levels. So, think of a situation that you have some threshold, and then if the time series kicks above the threshold. So, let us say you have this progression, if whenever the time series hits above the threshold, you have a different model structure, and wherever the time series hits below the threshold, you have a different model structure. Okay. So, can you put forward a threshold value or a threshold level such that different dynamics are operating on either side of the threshold? Okay. And in this context, a threshold autoregressive model, or rather in short a TAR model, seems beneficial. Okay. Secondly, volatility models, which you already seen in the last week. So, again just to repeat, so generalized autoregressive conditional heteroscedastic kind of a models, or in short Gauch models, for modeling changing variance over time. So, again all these are sort of examples of non-linear processes again. Okay. Thirdly, non-linear dynamical systems. So, let us say deterministic chaos, right, and this is a very specific kind of a example in the literature, let us say Lorentz attractor. But again the idea is that again one need not go into details here. So, we will skip the details as to what you mean by Lorentz attractor, etc. But then you should understand that there should be some deterministic chaos in the model. So, deterministic chaos means some complex dynamics in the model or some abruptions in the model, etc. Okay. So, these are some of the examples when it comes to extending a linear time series process or a linear structure to a non-linear time series process. Okay. The next example could be from neural networks. So, let us say all these are examples, right. So, recurrent neural networks. So, I am kind of sure that almost all of you, or rather some of you, might have some confidence in analyzing neural networks, right. So, let us say RNNs or CNNs, right, or let us say LSTM, so long short term memory, right. So, all these examples are examples of neural networks, and again neural networks are not linear models, right. I mean there has to be some non-linearity in the underlying model. Okay. So, let us say LSTMs, RNNs, or some transformer based models for capturing complex dependencies, etc. And then next is polynomial and rational kind of model. So, let us say some non-linear regression models exist in literature, right, where one actually does some transformation. Let us say take some squares or some cubes of the variables which are included. So, again a small disclaimer when it comes to last point here is that in the regression literature you have some set of models which are transformed to a linear model, right, by taking square roots or taking squares, taking cubes, taking logs, etc. right. But all these are kind of examples of polynomial models or rational models. So, even if you have a polynomial structure, right, by transforming I can convert to a linear structure. Make sense? So, this is so I will say that this last point is sort of a subset of the non-linear processes. So, the model itself is not non-linear because one can actually transform it to make it linear, right. So, the correct way to put it is that all these are examples of polynomial regression models, okay, or rather non-linear regression models which are coming under the polynomial regression model heading. Make sense? So, all these are some of the important examples when it comes to let us say non-linear processes in general. So, again a small disclaimer here is that this is not, or rather these are not examples of non-linear time processes or rather time series processes, right. So, that word time series should not be included here. Okay. So, all these are examples of some non-linear processes in general. So, let us say neural networks, polynomial regression models, or volatility models, Arch-Gauch kind of a model, right. So, all these are called as non-linear processes in general. So, these examples should not be confused with are they time series models or are they not time series models, right. So, these are some general non-linear processes that exist in the literature, right. Okay, so now we will spend some time on explaining or getting into details about what do you mean by threshold models, right. So, the very first important kind of a model is called as threshold models. So, threshold models are a class of non-linear time series models. Now, again threshold models are pertaining to time series models, right. So, threshold models are a class of non-linear time series models where the dynamics change based on whether the process crosses certain thresholds or not. So, again as discussed a short while back, so let us say again imagine that you have some threshold here, some threshold value, right, and whenever the time series crosses the threshold, the dynamics change. So, it might happen that there might be some highly volatile nature, right, and as in when the time series again comes down the threshold or crosses the threshold one more time, there could be some calmness in the time series. Okay. Again this is one just hypothetical example. So, the idea is that on either side of the threshold different dynamics exist. Okay. So, just to again summarize this, the threshold models are a class of non-linear time series models where the dynamics change based on whether the process crosses certain thresholds or not. And secondly, they are particularly useful in capturing abrupt changes or regime shifts in the data. Okay. So, whenever you have some regime shifts or whenever you have some abrupt changes in the data set, right. So, they are particularly useful in capturing some abrupt changes in the data or regime shifts in the data. So, again do not worry, we will spend a whole lot of time on understanding what do you mean by regimes, what do you mean by regime changes or regime shifts in the model, etc. Okay. Okay. So, probably this is exactly where we spend some time on understanding what do you mean by regimes first, alright. But again the heading is key concepts in threshold models. So, we will again go deeper into understanding what do you mean by threshold models, understanding the different ideas or different characteristics of threshold models such as regimes or non-linearity, threshold variable, etc. Okay. So, the first ingredient is regime. So, what do you mean by regime? So, the time series operates under different regimes with distinct dynamics for each regime. Okay. Now, again just to simply put, think of a regime being a state in the time series process where different dynamics come into picture. Okay. So, again think of the complete time series or complete practical data which is broken down into these different states, and then these different states are called as regimes from a time series literature or time series context, right. And then these different regimes have different dynamics among themselves. Okay. So, two regimes need not be exactly same. So, there has to be some dynamic change when you shift from a regime to another regime. Okay. So, this is a small example, a small definition of what you mean by regimes. So, the regime is determined by threshold variable which may be the series itself or another related variable. Okay. So, this tells you as to how do you determine a regime. So, regime is determined by a threshold variable, there has to be some threshold variable, and then that threshold variable is nothing but that thin line between any two states. Okay. Again just to give you one visual example or one visual appreciation. So, let us say you sort of divide the time series into different states. So, these might be the states or rather these might be the regimes, and then these vertical lines are nothing but the thresholds. So, think that these vertical lines are nothing but the thresholds everywhere, okay, and the behavior of the time series would have different dynamics in each regime. So, each subset here is one regime, alright. So, overall you have 4 or rather 5 different regimes, and as in how a time series crosses the threshold. So, let us say something like this, the dynamics might change. So, in this regime it might happen that the time series is highly volatile, but again as it crosses a different threshold it might happen that again the time series is calm, again it might happen that in the next regime the time series is highly volatile, etc. Okay. So, again just to summarize, just to repeat one last time, is that regimes are nothing but different states of the underlying time series where different dynamics or different dynamical systems are persistent. Okay. Now, the next thing is threshold variable. So, this is that variable whose value determines the regime. Okay. So, again as discussed before, so all these vertical lines are nothing but the thresholds, let us say, right, and wherever you have a threshold and the moment the time series crosses that threshold the dynamics change. Okay. So, threshold variable is nothing but that variable whose value determines the regime. Often it is a lagged value of the time series itself. So, often the threshold value is nothing but a lagged value of the time series itself. So, let us say if you have yt, then yt minus 1 would be a threshold variable, or let us say yt minus 2 might be a threshold variable. So, as in how the time series sort of progresses or changes from yt minus 2 to yt minus 1 to yt, one can actually see different dynamics in the underlying time series. And next is non-linearity. So, these models exhibit piecewise linear behavior, making them interpretable while still capturing the non-linearity. So, the threshold models, the idea is that even if you break down into different regimes, so inside each regime it might happen that the model is linear, okay, but overall obviously the model is non-linear. Okay. But then hence inside each regime, if the model is assumed to be linear by making some transformations or by the view of it or by the virtue of it, right. So, being linear inside each of the regimes make them interpretable while still capturing the overall non-linearity. So, hopefully this slide is kind of understood now, that what do you mean by regimes, what do you mean by threshold variables, and how does the idea of non-linearity or other linearity sort of ties all these things down. Okay. More on regimes. So, regimes and time series analysis refer to different phases or distinct phases or states of a system, each governed by different underlying dynamics. So, again I think the first point has been discussed number of times. Okay. So, if you split a time series into different states or different phases, where each state or each phase would be called as a regime, and then each regime is assumed to have some different underlying dynamics. Okay. So, in threshold models, these regimes are explicitly defined based on the crossing of thresholds by a variable, often the time series itself. So, again I think that we need not spend any much time on this slide, because both the points have been discussed number of times, that firstly what do you mean by regimes, and then what do you mean by threshold values or threshold models, right. So, again just to summarize one last time, is that whenever a time series crosses a threshold or a threshold value or a threshold level, then the time series enters into a different regime, right, and which means that there is a dynamic shift, or there is some shift in the dynamics of the underlying time series. Alright, so now we will try to understand that what exactly are some of the regime characteristics, right. So, the first one is distinct dynamics. What do you mean by that? So, each regime has its own set of parameters and equations that describe the behavior of the system. So, each regime is sort of distinct, and each regime has a distinct dynamics. Okay. What do you mean by that? Is that each regime has its own set of parameters and equations which describe the behavior of the overall system. For example, economic growth rates might follow one pattern during expansion and a different one during recession. Okay. So, again this is a very easy to understand sort of a example, where let us say if you are talking about economic growth rates, and then here how many regimes are we talking about? We are talking about two regimes. So, the first regime would be expansion, the second regime would be recession, and obviously expansion and recession are completely different. So, they have different dynamics altogether, right. So, for example, economic growth rates might follow one pattern during one of the regime, which is expansion, and a different pattern in the other regime, which is recession. Okay. Secondly, transition mechanism. So, what do you mean by transition mechanism? So, regimes change based on specific rules or conditions, such as crossing a threshold or a probabilistic switching mechanism, right. So, we have to understand that how does the time series kind of switches between regimes. Okay. So, often at times, or rather almost every time, regime changes are based on specific rules or characteristics or conditions, such as crossing some threshold value, right, or more from a probabilistic switching kind of a mechanism. So, we will try to understand what do you mean by this probably in coming slides or maybe coming lectures in this week. Okay. But then again, hopefully crossing a threshold should be understood as of now, right. So, we spend quite some time in understanding as to how the regime switches happen. So, time series switches from one regime to another based on some, let us say, threshold values, or it could happen that is based on some probabilistic kind of a switching mechanism in place. Okay. Next is temporal persistence. So, regimes often persist for a period before transitioning, leading to clustering of similar states. So, what do you mean by that? So, I will give you an example. So, let us say this is the time series. I will only broke this entire time series into two different regimes. So, this is the threshold value, let us say, and this is the behavior of the time series here. So, let us say the time series behaves like this, and then the moment it crosses the threshold, you can see that the time series behaves, which is highly in a volatile sort of a nature. Okay. But again, if you see, or if you sort of look inside each of the regimes, so let us say this is regime 1 R1, and this is my regime 2, which is R2. Okay. So, overall you have one threshold value, which is this. So, this is T1, and then two regimes on the either side of the threshold. So, R1 and R2. Now, if you focus your attention into either of the regimes, let us say R1 for that matter. So, if you focus your attention in R1, so the time series behavior has some persistence within each of the regime. What do you mean by that? So, regimes often persist for a period before transitioning. So, before you see this transition, you see that the time series is sort of behaving in a persistent kind of a manner. So, persistence means that there is some long memory property, right. Long memory means that there is some sort of a behavior which repeats itself over a while basically, and same characteristic can be seen in the second regime as well. So, if you shift your attention to R2 here, so since the time series being highly volatile in R2, same sort of, or rather the exact same kind of a characteristic can be seen throughout that entire regime. Make sense so far? So, again I can give you a counter example. So, counter example could be, let us say again I will redraw the exact same sort of a graph, where you have one threshold value, two regimes, right, and it might happen that the first R1 is exactly same as what we had earlier, but the moment the time series transitions to R2, it is highly volatile initially, but later on the time series is not that volatile, and this might not be the case. Okay, so this might not be the case, and why? Because inside any of the regimes, the time series should be persistent. So if it's sort of following this highly volatile nature, it should be persistent over a while. Hopefully this is clear. So this is one of the regime characteristics, right? And the second characteristic is non-linearity. So the overall system may appear to be non-linear because of abrupt or smooth transitions between the regimes. Okay. Now again, we will quickly try to understand that what exactly the types of regime transitions. So the first one is called as abrupt transitions or discrete switching. So changes between regimes are instantaneous when a threshold condition is met. So whenever the time series hits a threshold, then it sort of switches the regimes instantaneously. So this is called as abrupt transition. So transitioning from one regime to another. Okay. And some of the model examples in this context are threshold autoregressive or TAR, or self-exciting TAR or SE-TAR. So these are some example models under the abrupt transition kind of a framework. And some of the use cases could be economic recessions and recoveries, sudden market crashes or booms, etc. Okay. Now the other kind of a transition could be smoother transitions or called as smooth transitions. So changes between regimes occur gradually over a range of values of the threshold variable. So here the difference is that the changes are not abrupt, as we saw in the earlier slide, right. So you have a large difference between abrupt transitions and then smooth transitions. So what are the examples here? So you have the star kind of model. So smooth transition autoregressive models, or in short star, or logistic or exponential transition functions. So these are some examples. And use cases could be gradual policy shifts, for example changes in monetary policy effects, or transitioning between weather patterns, etc. And the last kind of a transition would be probabilistic transitions, where regime transitions are governed by some probability or other probabilities, often modeled as some latent variables. For example, Markov switching model. So again, Markov switching models, the transition is neither abrupt nor smooth, but all these transitions are governed by some external probabilities, okay, where you have some external random variables in play, or so all these are called as latent variables, right. And one very useful model in this context is called as Markov switching autoregressive, or in short MSAR models. Couple of use cases could be stock market volatility clustering, or hidden states in biological systems, etc. Okay. Alright, so again just to understand that where we are sitting at the end of the first session of this week is that we tried to delve deeper into this entire idea about non-linear time series processes, understanding the characteristics of those, understanding what you mean by regimes, how do regime switches happen, right, and what are the three different kinds of regime transitions in play. So abrupt transitions, smooth transitions, and probabilistic kind of transitions. Okay. Thank you.